Okay, let us continue. So, our aim is to find geodesics on a surface of revolution, which is parameterized by sigma u v, f u cos b, f u sin v g u. And what are the assumption? We assume that f u is greater than 0, so that the curve does not come here in the board, curve is does not intersect the z axis, and we will take. So, my curve gamma is f u 0 g u, I will take it as usual a unit speed, that is df du square plus dg du square equal to 1. Okay. We just recall it was a exercise problem, assignment problem, or I did it myself, I did not remember. The first fundamental form of sigma is simply du square f u square dv square, that is E equal to 1, f is 0 and g is f u square. Okay. So, what happens to geodesic equations? E is 1, f is 0. So, this part E u u is this 0, f u is 0 and g u is g is f u. So, g u is f u square. So, that is u dot dot left hand side equal to, so g u v dot square, but g is f u square. So, this is simply f u half is there. So, f u df du applying chain rule v dot square. What happens to the geodesic equations 2? F is 0, g is f u square, this is 0, this is 0, g v is there, so it will be same as. So, it is saying d dt of f u square v dot equal to 0, because right hand side is 0, right. G v is 0, because g is a function of u only. So, this right hand side becomes 0, g is f u square, v dot d dt of this thing is 0. Okay. So, we want to find unit speed geodesics. So, let g be such. Unit speed geodesic. What it means? 1 equal to g dot t square. Now, calculate what is it? Sigma u t v t is given to us. So, this will be simply u dot square plus f u square v dot square. Why is so? I mean, you can check. G t is sigma u t v t. So, g dot t is equal to sigma u dot plus sigma v dot. So, g dot t norm square is sigma u dot plus sigma v dot, inner product is same, sigma u dot, sigma v dot. But now see, you calculate sigma u is what? Sigma u is fu, sigma u is prime. So, df du cos v, df du sin v, and then dgu du. Similarly, calculate sigma v, calculate the cross product terms, you will get this expression. I mean, you have to use that gamma is unit speed. So, you may wonder that what happens that here is df term comes up, but when it is multiplied there will be df du square, and because of sin and cos there will be dg du square, but we have already assumed that df du square plus dg du square equal to 1. So, use that, you will get this condition is there. Let us put this condition as star. Okay. So, you do the calculation yourself, no problem. Now, let us continue. How do I find the geodesics? First, suppose I go very humbly, I look at v equal to v naught, that is a meridian. Here in the picture, v equal to v naught is a meridian. So, v naught some constant. Okay. Is GE1 satisfied? Satisfied by this fellow. So, if I have v is equal to meridian, so this right hand side is 0 because b dot is 0 because v is constant. So, I have u dot dot equal to 0 and u dot square equal to 1. Satisfied provided u dot square equal to 1 from star, that is u dot equal to plus minus 1. So, suppose u dot is plus minus 1. So, I have v equal to v naught and u dot equal to 1 or minus 1. Is G2 satisfied? Well, sure, because v dot is 0. So, this side is 0, this is 0. So, G1 and G2 both are satisfied. You understand what is happening? If I have v dot equal to 0 and u dot equal to plus minus 1, then G1 is satisfied, and if v dot equal to 0, G2 is automatically satisfied because v dot is 0, right hand side is 0. So, this says G2 is also satisfied. Says what? This is if and only condition, any curve satisfying G1 and G2 is a geodesic. So, this says any meridian is a geodesic. Provided I have taken gamma to be unit speed, that is important. Huh? Okay, let us look at the parallels. U equal to u naught, some constant. So, this gives a parallel. What will happen if u equal to u naught? In star, this is 0. So, I will have from star will give us f u square v dot square equal to 1, which gives v dot equal to plus minus 1 by f u naught. This should not be equal to 0, but that is not equal to 0, we have assumed f not equal to 0 always. So, when is G 1 holds? Look at G 1, V dot equal to plus minus V dot square equal to 1 by f u square, u dot equal to 0. So, this holds, G 1 holds if and only if df du thus has to be 0. That is, if and only if f u is constant, but this constant is has to be f u naught, because I have fixed u to be at u naught. So, then G 2 also holds, because I for this, hence a parallel is a geodesic provided f u is constant. So, in my curve gamma here, this is my curve gamma, this f u should be a some constant c. So, that but that will force G u square right. So, G u is also, and G u I want a smooth function. So, G u will also force to be constant. No, sorry. That will force dg du square equal to 1. So, dg du equal to plus minus 1. So, u to be a straight line, G to be a straight line. So, parallels in general are not constant, are not geodesics, unless this in gamma u the first part f u part is constant and G u is just a straight line. So, when it is so, what will be the situation? The situation you see okay, f u has to be constant and G u has to be a straight line. So, this gamma curve has to be a line, and in that case what I will get? I will get a perfect cylinder. So, only in the case of cylinder parallels are geodesics, and that we have proved it last class, last to last lectures. So, here in cylinder these parallels are actually geodesics. It has to be, because this now we have also proved through geodesic equation. Okay. This is also the reason why something happens in the sphere. Well, for sphere I should take this to be the curve. So, gamma u I should take cos u sin u, sorry 0 sin u. Here f u part is not constant. Well, I had some condition, right, I mean I should not touch the z axis, okay, does not matter, because after all if I remove little bit, I do not complete the curve, the parallels are not going to be changed. I will still get the sphere maybe with a hole through the north pole to south pole. So, I will get the globe, our globe in general. but here the parallels are like this, but they are not geodesics, but meridians are geodesics. So, these are not geodesics, because Fu is not constant and GU is not straight line. This has a far reaching consequence for finding the line of flights. If suppose I have a long distance flight, it will try to find, it will try to follow the geodesics, because as we will see in one of the next lecture, maybe next lecture, that geodesics are actually the shortest path between any two points. Now, so for long distance flights, so they will try to fly along the meridian, to join along the meridian, so that they has to travel shorter path, because if they travel around the parallels, they have to cover much more, because the shortest path is always the meridian, along the meridians. Okay. So, this shows on the surface of revolution I have meridians parallel, meridians as geodesics and parallel geodesics only for cylinders. So, in general the question remains, what are all geodesics? On assumptions are same, gamma is unit speed. Okay, I cannot answer it, we cannot answer it from this geodesic equation alone now. So, special case we can, looking at meridians and parallels. For that we need a deeper theorem, it is called the Clairaut theorem. Okay. The proof involves geodesic equations again, but let us see the statement. So, gamma be a unit speed geodesic. On a surface of revolution this is for surface of revolution only, okay. Equal to this fellow with assumption Fu is, I can take greater than or equal to 0, does not matter for Clairaut's theorem. Psi be the angle between gamma dot and meridian of sigma. So, I have taken a point, okay. At that point I am looking at, I am trying to find out geodesic passing through that point. Let us take a very simple curve, I am rotating it along z axis. Okay. Here is a meridian passing through some point P. Okay. Gamma be another curve which is also passing through P and maybe this direction, and psi is this angle. So, this is the tangent on the meridian, maybe I use different color chalk. This is a tangent on the meridian, this meridian, and at P, and this is gamma, this is tangent to gamma, this is gamma, tangent to gamma, gamma dot at point P. So, I am looking at this angle psi. First conclusion is then fu sin psi is constant around gamma. Conversely, if fu sin psi is constant along some unit speed curve gamma and no part of gamma is a part of some parallel to sigma, then gamma is a geodesic. Okay, what is this quantity? Suppose you are travelling around a geodesic. What is fu sin u? If you are travelling around a curve gamma, then fu sin u, sin psi, if psi is this angle, this is just the angular momentum in kinematics. And what it says, to be a geodesic, angular momentum must be preserved. Otherwise, and if angular momentum is preserved, if you are travelling along a curve, preserving the angular momentum, and you are not travelling parallels, because parallels are ruled out from the previous observation, then you are actually travelling through a geodesic. We will not prove this theorem. But use it to find geodesics on surface of revolution like this. For today's class lecture, I will end with 2 exercises, and the next lecture we will consider a particular type of surface which is very important and which starts one area of geometry, so called hyperbolic geometry. But for today, so again consider fu cos v, fu sin v, gu with all the condition, even so gamma u fu 0 gu fu greater equal to 0, gamma dot u is 1, unit speed, everything, f g smooth. Consider the Gaussian curvature, what we defined this week. Kg is product of two principal curvatures. Exercise first, show Kg is minus f double dot dot f dot. So, f dot is df du with respect to u. This will be easy. Second is also easy, but be careful while doing this part. If Kg equal to 0, that is Gaussian curvature is 0, then by applying rigid motion in R 3. So, determine the reservation, determine which are the reservation. Not the, because there are cases. We have sigma is either a circular cylinder or xy plane or part of a cone. So, Gaussian curvature is 0, then I can only have up to rigid motion 3 surfaces: circular cylinder, xy plane and part of cone, by surface of revolution of course. I mean surface of revolution can be only these 3 cases. Third part of the exercise, suppose the Gaussian curvature is constant 1 plus 1, then by applying rigid motion so up to rigid motion sigma is part of a sphere. So, sphere is the only surface of revolution which has constant Gaussian curvature 1. Remember, for sphere we show that k 1 and k 2 both are 1. For cylinder k 1 is 1, k 2 is 0. Okay. And next class, next lecture, so this is for next lecture. This is what I said, that the beginning of a new geometry, we will consider the surface with constant Gaussian curvature negative, and we will see one such, in fact prototype of such a surface, and try to calculate the geodesics on that surface. For instance, you know, for circular cylinder, xy plane, part of a plane, cone and sphere, we know all the geodesics. For circular cylinder we know is straight line, circle or circular helix, xy plane are straight lines only, part of a cone, these are meridians. If I, these are meridians, and for sphere of course we know the great circles, but here things will be quite different. We will see it in the next lecture. Thank you.